Welcome to this lesson on understanding variables in scientific experiments. Today we're going to learn how to clearly define independent, dependent, and controlled variables. Before we dive into the details, let me explain why understanding variables is so crucial to good scientific methodology. Variables are the foundation of every experiment. Without clearly defined variables, your results will be meaningless and unreliable. Confusion about which variables you're changing and which you're measuring can lead to completely invalid conclusions. This is one of the most common mistakes in experimental design. There are three main types of variables in any experiment. Let's define each one carefully. The independent variable is what you deliberately change or manipulate in your experiment. This is the variable you control. The dependent variable is what you measure. It depends on the independent variable. This is your outcome or result. Controlled variables, also called constants, are everything else that must be kept the same throughout the experiment. These ensure a fair test. Here's a helpful analogy to remember the difference. Think of a puppet show. The puppeteer is like the independent variable. The puppeteer controls and manipulates the strings. The puppet is like the dependent variable. It responds to what the puppeteer does. The puppet's movements depend on the puppeteer's actions. Similarly, the dependent variable depends on changes in the independent variable. Let's work through a concrete example. Imagine you want to test how the amount of water affects plant growth. You have 4 identical plants. You give each plant a different amount of water, 50 milliliters, 100 milliliters, 150 milliliters, and 200 milliliters per day. So here's a question. What is the independent variable in this experiment? The answer is the amount of water. This is what you are deliberately changing across the different plants. Next question. What is the dependent variable? The dependent variable is the plant height or growth that you measure. This depends on how much water the plant receives. Now, the critical question. What variables must you keep constant? You must keep everything else the same. Same type of soil, same amount of sunlight, same temperature, same type of plant, same size pot. If you don't control these variables, you won't know if differences in growth are due to water or something else. Let me show you what happens when you fail to control variables properly. This is where experiments go wrong. Imagine you give both plants 100 milliliters of water, but one is in clay soil and one is in rich soil. The plant in rich soil grows taller. You might incorrectly conclude that water amount affected growth. But wait, you gave them the same amount of water. The actual problem is that soil type was not controlled. The difference in growth was due to soil quality, not water amount. Your experiment is now meaningless. This is exactly why controlling variables is absolutely critical. One uncontrolled variable can invalidate your entire experiment. Let's look at another example from physics. You want to investigate how surface roughness affects friction force. You pull a block across different surfaces, smooth wood, rough sandpaper, and carpet. You measure the force needed to move the block. The independent variable is the surface type or roughness. This is what you're deliberately changing. The dependent variable is the friction force required to move the block. You measure this with a force meter or spring scale. What must be controlled? The block mass, the pulling speed, the angle of pull, and the block material. If you change the block mass, friction will change for that reason, not surface roughness. In this friction experiment, there's actually a quantitative relationship we can explore. The kinetic friction force equals μk times the normal force, where μk is the coefficient of kinetic friction. The normal force equals mass times g, which is approximately 9.8 meters per second squared. If you don't control the block mass, then the normal force N changes, which changes the friction force. You wouldn't know if friction changed due to surface roughness or due to mass. Let's examine a chemistry example. You're studying how temperature affects the rate of a chemical reaction. You heat 3 beakers of the same chemical solution to 20 degrees Celsius, 40 degrees, and 60 degrees. You measure how fast the reaction occurs. The independent variable is temperature. You're deliberately controlling and changing the temperature. The dependent variable is the reaction rate. You might measure this as grams of product formed per minute, or as time to complete the reaction. What must be controlled? The concentration of reactants, the volume of solution, the pressure, whether you stir it, and the type of container. Let's look at what actual data from this temperature experiment might look like. At 20 degrees Celsius, the reaction takes 120 seconds. At 40 degrees, it takes 45 seconds. At 60 degrees, only 15 seconds. We can clearly see that reaction rate increases as temperature increases. This is a valid conclusion because we controlled other variables. There's actually a famous equation that describes this relationship quantitatively. The Arrhenius equation. The rate constant K equals A times E to the negative EA over RT, where EA is activation energy, R is the gas constant, and T is temperature in Kelvin. As temperature T increases, the exponent becomes less negative, so K increases, meaning the reaction goes faster. This equation quantifies what we observed. Let me highlight some common mistakes students make when identifying variables. Mistake number 1. Confusing independent and dependent variables. Remember, independent is what you control, dependent is what you measure. Mistake number 2. Forgetting to explicitly list controlled variables. Just because something seems obvious doesn't mean you shouldn't write it down. Mistake number 3. Changing multiple independent variables at once. If you change temperature and concentration together, you can't tell which one affected the result. Here's another helpful analogy. Think of an experiment like a detective investigation. A detective examines evidence to solve a crime. The detective controls which evidence to examine. That's like the independent variable. The evidence reveals clues about what happened. Those clues are, like the dependent variable, the outcome you measure. The crime scene must be preserved and not contaminated. If someone moves evidence or adds new items, the investigation is ruined. That's like controlled variables. Everything must stay constant except what you're testing. Let's do one more detailed example. You're investigating what affects the period of a pendulum, the time for one complete swing. Here's a simple pendulum. A mass hangs from a string of length L. You pull it to the side and let it swing back and forth. What could you choose as your independent variable? There are several possibilities. Option A. You could vary the length of the string and measure how period changes. Option B. You could vary the mass of the bob hanging on the string. Option C. You could vary the amplitude, how far you pull it to the side initially. Here's the key insight. You must test one variable at a time. If you change length and mass together, you'll get confused results. Let's say you decide to test how string length affects period. Let's set up this experiment properly. Independent variable is the length of the string. You'll test different lengths like 0.5 meters, 1 meter, and 1.5 meters. Dependent variable is the period T. You measure the time for one complete swing using a stopwatch. Controlled variables. Use the same mass for all trials, pull it back to the same angle each time, release it the same way, conduct all tests in the same location to ensure G is constant. For a pendulum, there's a beautiful mathematical relationship between period and length. The period T equals 2 pi times the square root of L over G, where L is length and G is gravitational acceleration. Notice something fascinating. Period depends on length but not on mass. The mass doesn't appear in this equation at all. This is exactly why it's so important to control the mass. If you varied both length and mass, you'd find that mass has no effect. But if you didn't control it, you might waste time wondering about its influence. Let's calculate actual numbers to make this concrete. Let's say the length is 1.0 meter and G is 9.8 meters per second squared. The period equals 2 pi times the square root of 1.0 over 9.8, which equals approximately 2.01 seconds. If we cut the length to 0.25 meters, 1/4 of the original, the period becomes 1.00 second. Notice the period is halved when length is quartered because of the square root relationship. These quantitative predictions allow you to verify if your experiment was done correctly. If your measured periods are way off from these calculations, something went wrong with your controls. Now let me give you a systematic procedure for designing any experiment. Step 1. State your research question clearly. For example, how does fertilizer amount affect tomato plant growth? Step 2. Identify what you will deliberately change. This becomes your independent variable, in this case, grams of fertilizer per week. Step 3. Identify what you will measure as the outcome. This is your dependent variable, perhaps height of plant in centimeters or mass of tomatoes produced. Step 4. Make an explicit list of everything else that must stay constant. Don't skip this. Write it down. Same soil type, same water amount, same sunlight hours, same temperature, same plant variety. Step 5. Design exactly how you'll collect data. How often will you measure? What units? What instrument? How many trials? Understanding variables isn't just academic. It has profound real-world implications. In medical drug trials, researchers must control variables incredibly carefully. If they don't account for age, diet, exercise, and other factors, they can't tell if the drug works. In manufacturing, identifying which variables affect product quality is crucial. If a car company changes both the paint type and temperature simultaneously, they won't know which caused defects. Environmental scientists study how temperature, pollution, and other variables affect ecosystems. Controlling variables is extremely difficult in nature, but they must try to isolate effects. Let's do a practice problem. A student wants to test if sugar type affects how high a cake rises. The student bakes 2 cakes. One uses white sugar, the other uses brown sugar, then measures the height of each cake after baking. What is the independent variable? Think about it. The independent variable is the type of sugar. The student deliberately chose to use different sugars. What is the dependent variable? The dependent variable is the height of the cake after baking. This is what the student measures. Now the crucial question. What must be controlled? The same amount of flour, same number of eggs, same baking time and temperature, same oven, same size pan, same mixing method. What if one cake was baked at 350 degrees and the other at 375? Then you couldn't tell if height difference was due to sugar type or baking temperature. The experiment would be ruined. One more critical concept. You should always do multiple trials of your experiment. Why? Because there are random errors and measurement uncertainty in any experiment. One trial might give an unusual result by chance. If you measure the height 3 times and get 8.2, 8.5, and 8.1 centimeters, you can average them to get 8.3 centimeters. This average is more reliable than any single measurement. Multiple trials increase your confidence that the pattern you observe is real and not just a coincidence or error. Let's summarize everything we've learned about the 3 types of variables. Independent variable is what you deliberately change or control. Only change one at a time. Dependent variable is what you measure as the outcome or result. It depends on the independent variable. Controlled variables are everything else kept constant to ensure a fair test. List them explicitly. Good methodology starts with explicitly listing what will be changed, what will be measured, and what must be kept constant. Don't skip this step. Remember, confusion about variables leads to meaningless results. Your experiment is worthless if you can't identify what caused your observations. Understanding and controlling variables is the foundation of all scientific inquiry. Every major discovery in history came from carefully designed experiments where variables were properly controlled.